Today we are honored to welcome Dr. Ben Still from the UK. He is a physicist, author and educator. He's an honorary research fellow at Queen Mary University of London, and he teaches physics in school. He's written best-selling titles in both chemistry and physics, and today he's going to talk to us about his latest book, Particle Physics Brick by Brick, which has gotten great reviews. In this talk, he's going to try to cover the 14 billion year story from the Big Bang and to the periodic table of elements in 45 minutes using Lego. I like the level of ambition. Okay, so before I let him start, I will just like to mention that his book is sold here today in the back. The lady in the back sitting there, please wave at us. Yes? So if you like his talk, please make sure that you buy a copy, and maybe you have an aunt or a niece or somebody else that would like a copy as well, so buy a copy for them too. Okay, that was it. Welcome, Ben.
Okay, guys, so 45 minutes. I'm going to talk a bit about the standard model of particle physics, just to gauge the audience. How many people here are physicists? Okay, keep your hand up if you're a theorist. And experimentalist. Okay, cool. We got a good mix. And anyone not familiar at all with particle physics, or maybe seeing it for the first time, experiencing it for the first time? Okay, thank you, our cameraman. So I'm going to talk a little bit. This is very much a general talk, and it really much revolves around this word, analogy. So I'd like to start with the Oxford English Dictionary definition of analogy. And it says that it's a comparison between one thing and another, typically for the purpose of explanation or clarification. And in my mind, that relates quite directly to a scientific theory. In science, we are trying to devise scientific models in the language of mathematics which describe and explain nature. And so we can imagine that nature is this all-encompassing thing that science is striving to understand and developing mathematical models to be able to actually explain it in greater detail. So scientific theories are essentially a subset of that nature, and the whole idea of science is to push those scientific theories outwards and explain more and more of nature as we can. And I believe there's a room for everyday analogies when we're trying to teach scientific theories, certainly within a classroom and within a lecture. Everyday analogies, of course, break down very quickly, especially when we go to the more abstract ideas of particle physics and quantum mechanics. But there are certain strengths to be able to link our everyday experiences to these scientific theories, to develop students' knowledge. But the one danger is that we need to make students aware of the boundaries. The boundary at which these everyday analogies break down is very important. And I think it's quite important to discuss this with students if you're trying to teach new theories through everyday analogies, because I think also at the very real end of the spectrum, the progress of scientific theory is, again, knowing where those theories break down and understanding where the errors in our measurements are, and really where our theories are actually not able to explain the nature beyond a certain energy scale or below a certain length scale. And so I'm starting with analogy because this whole book is an analogy. This whole book is using Lego bricks to try and talk about fundamental particles. And in no way am I ever going to tell you that a brick is going to be a perfect representation of a fundamental particle. There is a point at which it breaks down. But I think what I've tried to do is stretch and extend an analogy as far as I can to cover as much of the scientific theory. So my everyday analogy of the Lego brick, I'm trying to explain as much as I can about the standard model of particle physics. So just quickly, we're trying to talk about the entire universe, which is quite difficult. But particle physicists split the atom down, and we get to a point where we can say that the entire visible universe around us is actually built from a small subset of building blocks. And those small subset of building blocks have been constructed into more complex things using quite a well-defined set of construction rules. And 99.9% of the universe around us is actually built from just a few building blocks. Things called quarks, up quarks and down quarks, and electrons. And then we have neutrinos. And certainly when I'm teaching students in high school, we only ever deal with these first generation of building blocks. But of course, there are 2 further generations of building block that have been discovered. Why there are exactly 3 generations, we don't know. We can't explain the why question. We can certainly discuss it, but right now, the Standard Model is just a mathematical framework which tells us how these fit together. The only difference, obviously, from these 2 generations is that they interact with the forces in exactly the same way, they just have a greater mass, which, in terms of the theory, means they're not stable. And that's why most of the universe is made from this first generation of particles. And alongside these building blocks, we have force carriers, we have the bosons, the things which exchange forces and interactions between these. And this also introduces the forces of nature. Gravity, I'll talk about in a second, doesn't really come into the Standard Model, but the strong nuclear force comes in and interacts with these quarks. The strong nuclear force, I'll discuss the colors in a second, and it's the reason that these quarks are colored and these particles here called gluons are colored. The gluons are the things which bind quarks into particles and also bind particles together within the nucleus. But it's only quarks which actually interact with this strong nuclear force. Then there's the electromagnetic force. The electromagnetic force, the force carrier is the photon, which I represent here by a little clear plastic brick. And this interacts with anything with an electric charge. So that's pretty much all of these building blocks, apart from the neutrinos. And then finally, there's the weak nuclear force. And this, as we will discover, is where it causes a lot of problems with a Lego analogy. But the weak nuclear force has a number of different force carriers, and it is the only thing which interacts with the neutrinos. But it interacts with all of these building blocks. And then there's something I'm definitely not going to be talking about, is the Higgs boson. But the Higgs boson is, again, another kind of force-carrying particle, which actually produces mass for these building blocks, and also the weak bosons. When all this is wrapped up together in the mathematics, it's the Standard Model of particle physics, and it's the scientific theory that I'm trying to explain in this book. And of course, as I've mentioned, Lego cannot give us the whole picture, but it can certainly take us quite far. So just quickly about the forces of nature. I mentioned gravity is the weakest force. It doesn't really come into play when we're talking about the masses of particles within the Standard Model. It's infinite in range, but we need things such as the size of planets to get an appreciable force from it. Electromagnetism has an infinite range and does come into the interactions of particles. Okay, those with charges, so not the neutrinos, but all of the others, interact with the electromagnetic force. So like charges repel, opposite charges attract. Then we get to the weak nuclear force, which is felt over a range of distances which are kind of constrained to the very nucleus of an atom, which is 0.001% of the entire atom itself. And then we get to the strong nuclear force. The strong nuclear force has an even more limited range and doesn't really go outside of the kind of width of a nucleon itself. And it's the things that keep quarks bound into particles and nucleons together in the nucleus. And I've listed them in the order of their coupling constants, or if you like, the strengths of the forces within the Standard Model. And these are important when we talk about the history of the universe in a second. So electric charges are assigned to these particles, and that just means that this is the way in which they interact with the electromagnetic force. So those of you familiar with the uptight quarks having positive 2/3 charge, minus 1/3 charge, this is to do with relative to the charge on the electron, or the proton, and the electron and its heavier versions, muon and tau, have a -1 charge, and neutrinos, as I mentioned, don't interact with the electromagnetic force because they have a 0 charge. And so, like opposite charges, I've mentioned, attract each other. And electromagnetism is, in a very real sense, what I would say is a one-dimensional force. You can put any charge, an electric charge, on a one-dimensional number line. Okay? It might be very positive, or it might be very negative, but whatever electric charge that particle has can be put on a one-dimensional number line. And of course, there is always a potential between two opposite charges, which actually draws them together. Again, we're much more familiar with gravitational potential wells, and so you can imagine balls rolling down the side of a valley and meeting in the middle, but these potentials exist between charges, and they therefore want to come together to form neutrality again. Something that's neutral will then not attract other charged particles. Another thing which we need to talk about is the fact that there isn't just one set of building blocks, there is two. We have the matter particles and we have antimatter antiparticles. And the difference between these two is that the way in which they interact with the forces is totally mirrored, it's totally opposite. And I'll explain in a second again why the colors have changed here on the quarks, but you'll notice the colors have also changed here. For instance, the electron has a negative electric charge, as we mentioned. The positron, or the anti-electron, has a positive electric charge. But not only is it the electromagnetic force which changes its interaction, but also the strong force and the weak force too. And so the electric charges are mirrored. So as I said, that mirroring point in the electric charge, because it's just a number line, the mirror point is what's positive is now negative, what's negative is now positive. And that's how you mirror the electric charge. It gets a little more complicated when you come to the strong force. Now, the strong force is not one-dimensional or two-dimensional. It's actually a three-dimensional force in the way I've been discussing. So you can't have just a single number line with positive strong charge and negative strong charge. That doesn't really work in the maths. And the analogy that was put forward and is used is that of the three primary colors of light, red, green, and blue, which mix together to make white. So if we imagine white as being our neutral in terms of strong charge, red, green, and blue being our different charges. If we take one of the primary colors away, we end up with a secondary color. Cyan is a mixture of blue and green, but no red. So cyan is actually can be thought of as the opposite of red because it's the total antithesis of red. Magenta, a mixture of red and blue, can be thought of as a total antithesis of green because there is no green in magenta. And yellow, which is a mixture between green and red light, can be thought as the total opposite of blue. And so instead of having a positive and negative on an axis, we have a primary color and a secondary color on the axis. So the opposite color charge of red would be cyan, blue would be opposite of yellow, green would be opposite of magenta, because they are the total opposite. In the same way that +1 is opposite to -1 in electric charges, the secondary colors are opposite in terms of the primary colors. And this allows us to form strong charge neutral particles. If you have 3 quarks, and if you have Lego in front of you, you can start building some of these. If you have 3 quarks, a red, a green, and a blue, then you form a neutral strong charge particle. And the way that we can do this, there's 2 ways we can do this with the first generation, is we can put 2 up quarks on top, 1 down quark on the bottom, and we form a proton. All 3 of these are legitimate protons. They are color neutral with respect to the strong force, and they're all protons because they have 2 up quarks on top, 1 down quark on the bottom. Again, we can form 2 down quarks and 1 up quark here, and we can form something called a neutron. So neutrons, again, are color neutral because they have red, green, and blue forming that white particle. And so all of these will be unidentifiable from one another because they form color-neutral particles. So it doesn't matter which way round you get your colors. If you've got 2 up quarks and 1 down quark in this shape, you've formed a proton. If you've got 2 down quarks and 1 up quark in this shape, you've formed a neutron. And so talking about those secondary colors means that if you also mix the secondary colors together, you again form a white neutral particle. Having all 3 secondary colors, you form a neutral particle once more. So there is also another way in which you can create neutral particles from those secondary colors, which, as I said, are the opposite to the primary colors. And so just to convince you, this is a nice little optical illusion. If you stare at the cross, you should see something moving around, a green circle. Now follow that green circle. It's not there. Your brain is putting the green circle where there is an absence of magenta. This is a nice optical illusion to show you very clearly that the way our brain constructs colors, green is the antithesis of magenta, and vice versa. Where there is an absence of one, your brain fills in green. Okay? It works very nicely with green and magenta. It's a little more difficult with the other secondary colors, but it's the same idea. And so with the 3 secondary colors, we can also build antibaryons. We are now using the opposite of the color charges, which means we are building with anticolors. And so those 3 anticolors can form antiprotons. 2 anti-up quarks and 1 anti-down quark forms an antiproton. two anti-down quarks and one anti-up quark will form an antineutron. But in the same way, they form colorless, strong charged neutral particles. And so, in this way, we can build both particles and antiparticles using quarks. There's another way, which I'm sure lots of you are aware of as well. You can combine a color with its anticolor. In a sense, it would be going one step along the axis and then going back to the center, where we are color neutral again. If you mix blue with yellow, remember yellow is a mixture of red and green, so it makes sense that if you mix yellow and blue, you get a color neutral particle once more. The same with red and cyan and green and magenta. So there is another way in which we can construct color neutral particles. You can construct them with a quark and an antiquark, a color and an anticolor. And we can form mesons. So the first generation of mesons, we can form pi pluses with up quarks and anti-down quarks. So again, you need to make sure that you have your anticolor. So blue would be matched with yellow, green with magenta, and red with cyan. But these are all legitimate pi plus particles. And then pi minus, again, is an anti-up and a down. And these all create color neutral, legitimate, strong force neutral particles. So this is where Lego analogy definitely breaks down, is the weak force. And it causes a lot of trouble, mainly because it involves transformation of particles from one to another. So particles are grouped into weak pairs, and the W bosons, which are some of the weak force carriers, actually change one particle into another, transforms between the weak pairs. Up quarks can be turned to down quarks, but only when they emit a W plus boson, and down quarks to up quarks with the emission of a W minus. This allows neutrons to turn into protons by ejecting a W minus, and this is what happens in nuclear beta decay. You can also go from a proton to a neutron, and we'll talk about this in a second, by ejecting a W plus boson. But these W plus bosons then themselves decay into other particles. And so creating Lego blocks from thin air obviously isn't possible. And so this is where the Lego analogy starts to break down. But we can still draw diagrams, Fireman diagrams, and things like this to show how the evolution occurs. And if you've got the right Lego bricks, it's still possible to follow some of these things. And so we can draw Fireman diagrams like this. So if you're familiar with Fireman diagrams, then you probably don't need the Lego analogy. But with the Lego analogy ingrained, I think it's sometimes easier to actually see visually how these particles are changing. As I mentioned, if the W minus is kicked out, then it may decay into an electron and an electron antineutrino. Protons can turn into neutrons, either by capturing an electron and forming an electron neutrino, or if the W plus itself decays into an anti-electron, a positron, and an electron neutrino. These processes are important in the story that I'm going to do, and I'm going to go through now. Because as was challenged in 45 minutes, I'm going to go from the Big Bang to the periodic table of the elements, and I've already eaten up probably half my time. So I've got to get into the story. This is my recreation of the history of the universe in Lego. Some of you might have seen something very similar from Fermilab. It's just it's a history of the universe, very biased by particle physics. Halfway is 10 seconds after the Big Bang. Then we zoom forward to 380,000 years, and then, cosmology. But I'm going to talk about these different stages of the universe from the Big Bang. I'm going to gloss over a lot of this initial stage, and we'll talk about that later. But the rest of the story we're going to go through quite quickly now, okay? So the first second of our universe, this is where I gloss over, lots of energy transformed into mass, into matter and antimatter and new particles. And the picture of the universe in the very early stages looked like this. There were some free quarks and electrons moseying around, and the universe was very hot, very dense at this time. The particles had so much energy, they were moving so fast, they could overcome all of the different forces of nature. But very soon after the Big Bang, the strong force took hold, because the strong force, as it's named, is very strong, and so the particles, even though they're traveling fast, can be bound by this strong force. And before the first second of the universe had ticked by, protons had formed. So quarks were no longer able to free stream and be by themselves. So protons formed within that very first second. And this was the picture then of the universe. A bunch of protons, some neutrons, and some electrons. The neutrons will decay eventually into protons, so I'm just going to focus on protons for now. But in the first minute, we needed the weak force to take hold, because protons, when they collide, can form something called a deuterium. Okay, it's a heavy version of hydrogen, a heavy version of the hydrogen nucleus. But for that to happen, we need one of these protons to change to a neutron, and we need that weak force to happen. And so, as you see, a positron and an electron neutrino is ejected, and we form a deuterium. So if you're playing along, then please do build. And then, in its lifetime, if a deuterium collides with another proton, it can form helium-3. Helium-3 is unstable. Okay, it doesn't last for very long, but in its short lifetime, if two of them met and collided within their short lifetime, then these two helium-3 would fuse together to form a stable helium-4 nucleus, and two protons will be spat out for the next evolution. And so in the early universe, we actually created the first light elements. And some of the other light elements were formed in smaller amounts, but I'm not going to talk too much about that. So this fusion process actually formed some of the light elements in the very early universe. But as the universe carried on from its Big Bang and it started expanding further and cooling further, the particles slowed down. And as the particles slowed down, the weaker forces of electromagnetism and gravity could start to take hold. And after the first minute, we had pretty much entirely protons and electrons with a few light elements smattered throughout. Then 380,000 years later, so we have to zoom ahead quite a while, the universe has cooled down a lot and expanded a lot for the next force to take hold, and that force is electromagnetism. And of course, negative electrons could no longer at this time move fast enough to overcome their attraction to protons. And so the electrons combined with the protons to form a neutral atom of hydrogen. The same thing with the helium nuclei, which was positive 2 charge. The two negative electrons would combine with the helium nucleus to form neutral atoms of helium. And for the first time, the universe was electrically neutral. So we're going from strong force neutral, using the weak force to build up some of those heavier elements, and now we're at electric charge neutral for the first time. And so after 380,000 years, the universe looked like this. It was now a collection of neutral atoms. There may have been some pockets where there wasn't neutrality, but on the whole, the universe was neutral. And some of you may know about the cosmic microwave background. This is the time which the cosmic microwave background was first able to free stream into the universe. And then, again, this is a very rough estimate. 400 million years later, we're talking about the first stars. And the clouds of gas had gathered so large that they had started collapsing under their own gravity, the weakest force. And in pockets in these clouds, they would collapse into a local center of mass. And as they collapsed in, they gained kinetic energy. They heated up. They heated up to the point where the electrons now had enough energy to escape that electromagnetic attraction once more and form a plasma, a collection of free electrons and free protons. They fell in even further, and they heated up even more to the point where they had the same heat and similar density to the early universe, where they were then able to recreate that fusion that happened in the first minute. And at the very center, this energy that was produced was starting to push out against gravity. This was a protostar. Eventually, so much of that fusion, so much energy was being produced, and it was pushing out against the gravity that an equilibrium was formed. The radiation pressure of the energy pushing outwards matched the gravity pulling inwards, and we formed a star for the first time. The fusion processes continued at the center where the temperature was high enough and the pressure was high enough for fusion to continue. And so what we saw in the first minute was going on inside these stars. There are other processes as well, other ways of turning hydrogen to helium. Now, I'm not going to go through the entire PP chain. If those of you know what it is, it's quite a horrific thing. But I'll talk about one other way in which hydrogens turn into helium. So if in its short lifetime a helium-3 collides with a stable helium-4, it can form beryllium-7. And thanks to the weak force, if an electron is captured by this beryllium-7, it will form lithium-7. One of the protons in beryllium has turned into a neutron to form lithium-7. Then, in its lifetime, if a proton collides with a lithium-7, it forms beryllium-8. Beryllium-8 is very unstable and quickly decays into far more stable helium-4. Again, we started with some protons, okay? Remember, we formed that helium-3 from protons in the initial stages. And again, we formed an extra helium-4 from where we started. This is another way in which those protons got built up into some of the heavier elements. This was all happening, burning hydrogen, fusing hydrogen to helium in the very main sequence of the star's life, which is the majority of its life, to be honest. If a star is large enough, then once a lot of this hydrogen fuel is used up, then the fusion process is slow, gravity wins out, and gravity crushes the star in. As it crushes the star in, it gives the particles at the center more kinetic energy. It heats up. The pressure increases. And if the pressure increases and the heat increases to a certain extent, then it could be the point where two helium get close enough and when hit with enough impact to fuse. But we've said that it forms beryllium-8, which is unstable. And so beryllium-8 can decay again to helium-4. Not very interesting. But in its short lifetime, if beryllium-8 collides with another one of the helium-4, because the helium-4 content is high enough, then it can form carbon-12, which is a stable nucleus. And it's in this way that the stars are producing heavier elements. And again, I go through it in much more detail in the book, but after the carbon-12 has been built up, these helium-4 can keep colliding with the heavier nuclei in something called an alpha ladder. So a helium nuclei can collide with the carbon-12 to form oxygen-16. Again, oxygen-16 can collide with the helium-4 to create neon-20, and so on and so forth. And in this way, the star builds up to heavier and heavier elements, ending at iron-56, or ending towards nickel, and then to iron at iron-56. There are other stages in between. For instance, the helium content gets dwindled a bit, and what happens is this neon or some of the heavier elements need to be split apart into helium-4s again to reignite the star and to create heavier elements. But really, this is what's happening at the core. And you can create all of these elements with this Lego model. It kind of follows the same thing. Trust me, uranium gets a bit unwieldy. You end up with a very, very tall stack. But using the basic building blocks we talked about and using the basic construction rules, you can get to every element in the periodic table, and you can construct it. And so I hope I've convinced you that you could build every element. Of course, elements heavier than iron are produced in supernovae and hostile environments like that. But again, I've talked about that as well. They can capture neutrons, and then they build up to heavier elements that way. So I'm going to wrap up now, because I think I'm getting to the end. And I just want to talk about the fact that I mentioned the Lego analogy has an obvious horizon, and horizons are part of physics. Horizons are where the most exciting physics occur, of course, because at the horizon, it's where you're actually doing cutting-edge research and you're pushing forwards to try and understand more of nature. And you're doing that in a very real sense by developing, in a mathematical language, an analogy of nature. And so the standard model is well known to have flaws. I glossed over this bit down here because the standard model can't talk about this part of the history of the universe, simply because it has a high energy cutoff. And so when the energy is too hot and too dense, it can't be explained using the standard model. And this it's called the Planck scale, and this very well-known energy limit to the standard model is what we're trying to find theories that go beyond. We're also trying to find evidence through experiment that goes beyond that Planck scale and takes us beyond the energy levels. And so in a very real sense, not only does Lego have a horizon in terms of analogies, but the standard model does too. And that's where the excitement comes in playing with analogies, is trying to develop new ideas and new theories. And when I teach physics in class at schools, the way in which you can really challenge physics students is by giving them analogies and asking them to tell you where it breaks down. And that gets them then talking about how science actually works and how you can develop scientific theories into a new idea and maybe push the boundaries a little further. So, thank you very much. Yeah, so if you guys have got any questions, then I think Ellie's going to come around with a roaming mic. I'll try and answer them as best I can. Sorry. No?
No questions?
Stunned silence. Does everyone just want to play with
Everything
Lego?
was clear then.
So there is a box. So the Lego we've got on the table was to kind of do some of the things which I was talking about in the standard model. But if you want to be a theorist and you want to play with some weird and wonderful Lego, there's a box at the back as well for you to come up with your own ideas and theories beyond the standard model. And there's some really cool pieces in there. So.
Okay,
No
if there's no questions, we will thank Ben again.
Okay, thank you.
And here we have a little gift from the University of Oslo. It's
Oh.
nothing much, but there you go.
Thank you very much. Perfect for coffee. Essential in physics.
And also you said something about signing, right?
Yes, if anyone has purchased the book and they'd like it signed, I'll nip towards the back and I'll sign copies of the book as well if you're interested.
Okay, thank you all for coming.
Thank you. Cheers.